But there is baseball.
Hello, everyone, and welcome to the review session for our first exam, Power System Analysis class. This exam will contain everything that we have up to the previous class, lecture 6. So everything from the beginning up to lecture 5 is going to be included in this exam. So we're going to have phasor and complex numbers, conversion, a little bit of complex numbers, how to calculate complex numbers, and power factor also is a part of it, and eventually per phase unit and analysis of line transmission systems. So without further ado, let's start with the first question. Again, you know how this works. I will give you a few minutes, 5 to 10 minutes. The first student to solve this is going to get extra points. And the first question is, given Z1 equal to 6 plus J8 and Z2 is 3 minus J4, we want to find Z1 divided by Z2. Have you finished? What is the answer?
Negative 0.56 plus J1.8.
Yes. Yes. Did you convert to phasor and then back, or you just did it? Okay. So there are two ways to solve this. The first way to solve it is to convert this to a phasor mode. So 6 plus J8, R is going to be equal to square root of A squared plus B squared, and the alpha or theta, say theta, would be equal to tan inverse of B over A. And when you find that, you can easily divide them. Another way to find it is to multiply the numerator and the denominator with the numerator and the denominator by the conjugate of Z. So what we do is it's going to be 6 plus J8, and you can do this when it's not a very complicated, complex number. So it's going to be 6 plus J8 times 3 plus J4 divided by 3 minus J4 times 3 plus J4. So this is multiplied, both sides are multiplied by Z2 conjugate, the denominator and the denominator. And when we do that, we're going to get 18 plus J24 plus J24 plus J squared 32. We know that J squared is equal to negative 1. This divided by 9 plus 16. Now, if we simplify that, it's going to be negative 14 plus J48 divided by 25, or it's going to be equal to negative 0.56 plus J1.92. Another way, again, is, for me, This is the easier way, but some students prefer to convert it to phasor and then divide it. Obviously, when you divide r with the degree of theta, r1, and r2 with the degree of theta 2, it's going to be r1 over r2 with the degree of theta 1 minus theta 2. Did you write it down? Yes. Can I go to the next question? I want to, speed up so I can solve as many problems as I can. Now the next question, we want to compute z and express the results in polar form this time. Now z is equal to 2 plus j3 squared divided by 1 minus j in the power of 3. Okay, does anyone have the answer? Perfect. Anyone else? It is correct, but what did you find? Okay. Tyler, have you finished? Okay. Mm. You got one. Yeah, that's correct. Okay. Now, do you want me to solve it? Yes. Okay, so for the numerator, the numerator, I'm sorry, we want to find 2 plus j3 in the power of 2. We expand that. This is going to be 4 plus j12 minus 9, which is going to be negative 5 plus j12. Now, if you convert this to the polar form, it's going to be square root of 5 squared negative 5 squared plus 12 squared. So it's going to be 25 plus 144. It's going to be equal to 169, which gives us 13. And the degree would be tan inverse. This is R1 of B over A, which is equal to tan inverse or arctangent of 12 over 5. Yes, yes, thank you. Or we can do negative 180 degrees minus arctangent of this. But yes, that is correct because it flips. And this is going to be 112.6 degrees. Because it's in the second quarter. Now for 1 minus j in the power of 3, 1 minus j in the power of 3 is equal to 1 minus j times 1 minus j in the power of 2. Which gives us 1 minus 2j plus j squared. And we already know that j squared is equal to negative 1. So we can replace this with negative 1. And what we're going to have is going to be 1 minus 2j minus 1 minus 1. And this is, I'm sorry, this is for this part only. This, I don't want to confuse you. This multiplied by 1 minus j. And this would be equal to 1 minus 2j minus 1, which gives us negative 2j. So negative 2j times 1 minus j gives us negative 2j plus 2j squared. Because we have to multiply it by 1 and negative. Again, we know that j squared is negative 1, so the result here would be equal to negative 2j minus 2. Or negative 2 minus 2j. So this is the numerator and denominator. Let's find the final result. Now for negative 2z equal to, and by the way, if I've done one of the calculations wrong, just please let me know, because some of these I just do it in my mind. So if it's wrong in a part, just let me know. And it's, different from what you have. Now, the magnitude of z, which is our r, it's square root of negative 2 square plus negative 2 square, which gives us square root of 4 plus 4. It's square root of 8, which could be written as 2 with the square root of 2. Now, tan inverse of negative 2 over negative 2 is 45 degrees. And because both of them are negative, and as you know, what is tangent? How do we calculate tangent? I'm sorry, louder. Yes, opposite over adjacent. So when it's -2, it means it has a 180 degree, when it shift, because it's on the in the it's in the third one, two, three. Yes, and this is in the third quarter. So this could be written as theta would be equal to, by the way, this is theta. It's going to be 180 degrees plus 45 degrees, which gives us 225 degrees. Or we can write, it's going to be equivalent to -135 degrees. Both of them are the same. So you rather go this way or you're going the opposite direction. Both of them are equal. So if we could write like this, 2 with the square root of 2, 225 degrees, or the equivalent form would be 2 with square root of 2 with the degree of -135 degrees. Now that we have the first one, what was the first part? It was 13 with the degree of 100 and so the first one was 13 with the degree of 112.6 degrees. So Z would be 13 with a degree of 112.6 degrees. And the denominator would be 2 square root of 2 with a degree of -135 degrees. So it's going to be 13 divided by 2 square root of 2 gives us 4.596. And 112 minus -135 gives us 247.6 degrees. We can write alternatively, like subtract 360 by 247.6, and that's going to be a negative degree, but both of them are correct. Now, did you write this down? You already got this. Most of you got this. Can I go to the next question? Yes? Okay. So next question, it's about line drop and source power, resistive load. As load of 100 ohm is supplied at 40,000 volts with 0 degrees through a line impedance of 5 plus J 40 ohms. Find line current I, the sending end voltage, which is the generator, Vs, and the complex power supplied by the source. So the complex power of the source. So again, as mentioned, we have a source, which is 40,000. I'm sorry. Which is unknown. And we have the impedance of the line, which is 5 plus J 40 ohms. And we have the load voltage, which is at 40,000. Vs and On the exam, you're going to have something very similar to these. I would just change the numbers. Maybe, add another part. Oh, by the way, Z load, this is 100. Wish I did everything with red. It would be much easier. Here we are. Has anyone solved it? So what is I? Perfect. What is VS? Perfect. And what is S? Okay. Megavolt amp. Yeah, okay, the complex power unit image. Yes, pretty close, that one, but the rest is correct. Thank you. So first thing, we want to find the current. And the current using Ohm's law, it's going to be the load voltage over the load impedance, which is 40,000 with a degree of 0 degrees over 100 with a degree of 0 degrees gives us 400 amps with a degree of 0 degrees. So this is our current, first part. Now for the second part, I can simply write a KVL. And for this KVL, I'm going to call it KVL number 1. For KVL number 1, if I write it's going to be Vs would be equal to V load plus IZ of the line. And since all of them are series, the I is the same in both of them. So Vs would be equal to 40,000 plus 400 with a degree of 0 degrees, so it's going to be 400, and we don't have any j because the degree is 0 degrees, times z line, which is 5 plus j 40. Now, Vs would be 40,000 plus 2,000 plus j 16,000, which gives us 42,000 plus j 16,000. This is going to be our voltage. Now, if we want to find Vs in polar form, it's going to be square root of 42,000. I'm going to just put it in kilovolts plus 16,000 kilovolts. It's going to be equal to 44.9 kilovolts. Now, the degree of Vs is going to be tan inverse of 16 over 42, which gives us 20.8 degrees. So Vs would be equal to 44.9 with a degree of 20.8 kilovolts. Now that we have found Vs and I can find S, which is Vs I conjugate. So S would be equal to 44.9 with a degree of 20.8 times 400 amps that we had with a degree of 0 degrees. And we multiply 44.9 by 400 and add 20 with the 0 degrees. We get 17.98 with a degree of 20.8 degree megavolt amps. If you want to convert it to rectangular form, S would be equal to 16.8 plus J 6.4 megavolt amps. Both of them are correct. Did you write it down? Can I go to the next question? Yes. Let's go to power phase analysis. Yeah, power phase analysis. So a three-phase Y-connected source has a VAN of 1 with a degree of 0 degrees. That it feeds a delta-connected load with Z delta of negative J ohms through a line reactance of J.1 ohm per phase. The load needs to, the load node is also connected to a second delta-connected source with VA B of 1 with a degree of 0 degrees and another J.1 ohm per phase line. Find the load line voltage of VA prime B prime. Again, I will give you 10 minutes to solve this one. Yes, that's a phase voltage. Yes. Or line to neutral, or what we call phase voltage. So we have a VAB and VAC, which are phase-to-phase or line-to-line voltage. Yes, A to ground, to the neutral. Yes. I solved something very similar to this in the class. You can go back to the notes and use your notes from the class. The first person to solve this, I'll give extra points on their first exams. So I also added a hint over here. We convert delta to Y and line to phase before writing per phase KCL. I'm sorry? What I solve, I'm sorry? Yes, yes, sure. Of course, yes. We have plenty of time. We would definitely finish this one. But yes, of course. You can please go back to your notes if you have the lecture notes. We solved something very similar to this. And by the way, just a small hint, if you already remember this, but zy for a y connection is going to be equal to z delta divided by 3. So if you want to convert the delta impedance to y impedance, this is the equation. And you have to convert everything to y before you start. Okay, has anyone solved this? No? I'll give you a few minutes. Okay, so as mentioned, the first step is to convert all the delta loads to equivalent y loads. So zy would be equal to z delta, as mentioned, divided by 3. So it's going to be equal to negative j over 3. Now, VAN, the same thing. It's going to be equal to 1 over square root of 3, because the line-to-line voltage is square root of 3 VAN with a degree of negative 30 degree. We learned this on the previous classes as well. Now, we learned node voltage VA, and we apply KCL at point A. So it's going to be VA minus 1 with a degree of 0 degrees over j 0.1 plus VA with a degree of negative j over 3 plus, I didn't think this one through. Yes, we have to convert everything to a line voltage. I'm sorry. Yeah, that is correct. But the thing is, it's connected to a delta connection. So we have to convert all the deltas to y's and all the y's to deltas.
Delta line voltage is phase.
Yes, but in a Y connection, the phase voltage is different than the line voltage. So we have to find the equivalent line voltage here, because it's through one line that it goes. Let me finish it and I'll draw everything. So VA, I'm going to write the rest here. This is minus 1 over square root of 3 with a degree of negative 30 degrees over j 0.1, which is going to be equal to 0. Now, if we calculate this, and I've done a So again, I'm going to write it here. It's going to be VA minus 1 with a degree of 0 degrees over j 0.1 plus VA over negative j over 3 plus VA minus 1 over square root of 3 with the degree of negative 30 degrees over j 0.1. It's going to be equal to 0. We have to convert the rectangular form to polar form to be able to calculate this. And when we do that, VA would be approximately equal to 0.9 with a degree of negative 10.9 degrees volt. Now we will convert back to line voltage. So VAB is going to be equal to square root of 3 VA with a degree of 30 degree, and VAB is going to be equal to square root of 3.9 times 0.9 gives us 1.56, and the degree of VAB is going to be equal to negative 10.9 degrees plus 30 degrees, which gives us 19.1 degrees. So what we had, and I'm going to just briefly put in what happened here, is that we had this three-phase generator that is connected to a delta connection, okay? So when it's connected to a delta connection, what we have to do is convert all the delta to Y and all the Y's to delta. So we will convert Y to delta and delta to Y to be able to make a per phase unit like this. Z of transmission, Z load, and the generator G. That's the reason we did all of this. Now, we have 10 minutes. I want to solve another one. This is important. It's the bus power balance, complex power accounting. At a bus, the following powers are connected. Incoming line 1 is 90 plus 30 J megavolt amps. Incoming line 2 is 35 plus J 10 megavolt amps. Outgoing line is 40 plus J 10 megavolt amps, and local load is 40 plus J 20 megavolt amps. We find the required generator injection at the bus. This is from lecture 5, by the way. I'll give you a few minutes to think on it because we don't have a lot of time. Then I would start solving it. So what we have to do, the generators are going to have positive power, the loads, and also the output is going to have negative. And according to the KCO and Kirchhoff's law, the summation of everything must be 0. So the summation of generation number 1 plus summation of the input line number 2, number 1 plus summation of input number 2 minus S out minus S load, all of that is going to be equal to 0. Here we want to find the required generator injection, S gen. So S of the generator would be equal to S out plus S load minus S input 1 minus S input 2. This is a hint. I want you to solve the rest.
got a negative S gen, that means cut that.
Perfect. It means it has a net bus imbalance, and what it means is actually it requires power. It doesn't generate power. Okay. Let me solve this one as well. What did you get? The final number? What did you get? Perfect. Yes. So S generator would be equal to 40 plus J12 plus 70 plus J20 minus 90 plus J30 minus 35 plus J10. And if we add all of them, the generator's power, it's going to be 110 plus J32 minus 125, which gives us negative 15 minus J8 megavolt amp. So a negative result means the bus actually needs 15 megawatts and 5 megavolt amp reactive. Net import, not generation. Okay, so it's a net import instead of generation. So if in the exam there's like a multiple choice or something asking if there's export of power or import, it's the bus is the net importer of power. Okay. Thank you so much. I don't think we have enough time for another one. Yeah, I can give you one other one as well. This one, you can take a picture and you can solve it by your own. Power factor correction. A load is rated at 100 kilovolt amps with power factor of 0.8 lagging. It is to be corrected to power factor of 0.95 lagging. Find the required capacitor size, the compensator Q. Because you already had a question like this in measurement instrumentation, you already know this. I skipped this one so you can solve it, but it's going to be something like this in your exam. Okay, thank you so much. And again, next week we're going to have our exam. For the online students, I've already posted all the an announcement for that. In the meantime, if you have any questions, just please let me know. Thank you.